Good morning. We have been looking at aberrations, and we are going to start in this class looking at the specific monochromatic aberrations. We defined an aberration as basically the case or the time when a ray or how much a ray misses its paraxial image point. That amount is what we call the aberration of a system. And in yesterday's class, we looked at many different ways we can quantify that. There are several different ways that we can quantify that. And now we're going to look at specific aberrations. We also ended the class by saying how can we correct the aberrations, and we found that there are several ways that we can correct them, and of course the purpose is to be able to quantify them and then figure out how to minimize or even eliminate them in your optical system. Okay, so we start with spherical aberration. Spherical aberration is called sometimes as an on-axis aberration, and you can consider it to be a variation in the focus. So a variation in focus with aperture. Okay. What does that mean? Rays that come to a different location of the lens will focus at a different location on the axis. So normally we consider a lens, we take a lens and we say this lens has a certain focal length. We developed the equation for a lens. We said the lens focal length is 1 by f is equal to n minus 1 into 1 by r1 minus 1 by r2. So that gave us the impression that if I am using a single wavelength, so n is a fixed value, and I have taken one lens and I don't change that in any way, so the radii of curvature of that lens are the same, r1 and r2 do not change, this lens has one focal length associated with it, right? But what is going to happen in reality is that different rays, and when I say different rays, I mean the rays that hit the lens at different points. So you can consider each of them as coming at a different height, and therefore that's why we say variation with aperture, because they are at a different height. Each of those rays comes to focus actually at a different location. And that means you have a spread of the focus along the optical axis. Now in this figure, you have a convex lens, and you can see the paraxial rays, the rays closest to the optical axis. That's where we assume the ideal focus. They are the rays that will form the ideal focus. And you can see these rays, so of course the ray that's traveling along the optical axis, but just to make it clearer, let's take the ray just above the optical axis, and you can see that ray is focusing over here. So this point over here is the paraxial focus, and that's why this is been indicated as the paraxial image plane. As you go further and further away, so you go to this ray and so on, and you go to this ray, this is the topmost ray, and you can see this ray is coming to focus over here. So it's been exaggerated in this figure. The spread may not be this large, but this has been exaggerated to clearly show you that the rays coming from up here, so this ray, let's say this we call ray number 1, and let's say we call this ray number 10. Number 1 is focusing over here, and number 10 is focusing over here. So this spread, it's all focused, but then the overall result is that it's not focused, right? So as we talked about yesterday, so this is basically spherical aberration, a variation of the focus with aperture. It's an on-axis aberration because this is true for rays that are coming from on-axis points, and we will always consider a bundle of rays coming from infinity as coming from a single point. because they are from, if they're a parallel set of rays, they are coming from some one point, one direction, very far away from the lens. Okay. Now, we define or quantify, as we talked about yesterday, either with the longitudinal error or with this transverse error, or you could even talk about an angular error. Okay. With a convex lens, now when I say longitudinal error, we can go to the next. With a convex lens, we have what is called undercorrected spherical aberration, and that is the case where the rays from further away are being focused closer to the lens. That is undercorrected spherical aberration. So these rays are getting focused closer to the lens, and these rays are getting focused further away from the lens. That is undercorrected spherical aberration. Okay. Now, just a small aside, you will even notice in this figure that you have this bundle of rays that come and are incident on the lens, and then there's a region here where you have all these rays that have been refracted by the lens. So this is kind of an envelope. This last ray here is kind of an envelope, and beyond that, in this region at least, there are no rays. We call this the caustic, and you would have actually seen these caustics quite often. Right? Anytime you have a curved surface and light is incident, you see these caustics form. So they are really the envelope, and one side of that envelope, or what does it envelope? It envelopes a region where the reflected and refracted rays exist. It very clearly demarcates the region where those rays exist as opposed to where they don't exist, and it brings out very nice patterns. I just wanted to mention it because I'm sure this is a phenomenon that you would have really noticed anytime you have a curved surface, reflective dielectric surface. Very common in water bodies, and there you see a number of these regions because the surface of the water is not absolutely flat. There are variations. So each is acting like an individual lens, if you will, and its set of rays are being focused somewhere and causing a region where there are refracted rays and a clear region where there are no refracted rays. Right? There's a lot of people who study the mathematics of these because you get these nice cusp regions, and people who are looking to see how you can use this as some kind of diagnostic tool as well. So it's not just that it gives you pretty patterns, there are also people studying to see how it can be used for different applications. Okay, so I just wanted to bring that to you as a point of interest. Okay. Now, if I'm going to talk about spherical aberration or any aberration, we said we need to quantify it, and one of the ways to do that is to use what we call the ray intercept curves. So that's the RIC curves. Okay. So we can plot the RIC curves for different sets of rays. So what is plotted here, this figure, is a curve for the meridional rays. Now, let's look at the figure below here. We have a convex lens. The rays from further away from the optical axis have been focused closer to the lens. Those closer to the axis are focused further away from the lens, right? What is our error that we are plotting in these RIC curves? We talked about this yesterday. What were the axes? I said we never label the axis. What are we plotting? Tangential error was the y-axis and the x-axis was tan of the angle, right? And how did we plot? We said we always start by taking this ray first, and its error gets plotted, and so that's the first data point. Then the error of this ray will be the second data point, and so on. Which one is the on axis? I'm not, let's say 3, 4, 5, 6, 7. Let's say this is my on axis, and that's this data point, right? So what is the error that is being plotted in the RIC curves? You are plotting the transverse error, not the longitudinal error. You are plotting the transverse error. So if I look at ray number 1, its transverse error, the ideal focal plane, so B is the ideal focal plane. So this is where the paraxial rays are getting focused. So ray number 1 has a transverse error. Ray number 1 is this ray, but the paraxial focal plane is this. So its transverse error then is this. This is the transverse error of ray number 1 and its angle is this. So I will take tan u, that is this location on the x-axis. This x-axis, we call it the x-axis, but it is not a traditional x-axis in that it does not necessarily start from minus n and go through 0 to plus n. It just goes from that value of tan u for that ray and keeps on going for the values of tan u of the subsequent rays. Okay? So need not, depending on the rays you are plotting, it's need not going through a 0 origin. The origin here is the tan u. Of course, it is for the paraxial ray. Okay? If I look at, so this is the transverse error for ray number 1. Clearly, this smaller distance, let's do another color now. This distance is going to be the transverse error for ray number 2, right? So the transverse error is reducing, which is why this now corresponds to the transverse error for ray 2. And as you take subsequent rays are getting closer to the optical axis, the transverse error goes on decreasing. The ray that's on the axis has no transverse error, and then the rays from below, this is spherical aberration. You can consider your object point as on the axis or symmetrically seeing the lens. So you expect this curve that you developed in this region to be identical here, except it's flipped now because the values are positive. Okay? So this is a curve that we have drawn for spherical aberration for the tangential or the meridional rays. Now, in this diagram, I am drawing a convex lens and I have a set of rays incident, and I am showing you what happens when there's spherical aberration. But in an actual optical system, I'm never going to have the case where I say, oh look, here's spherical aberration. Oh look, here's coma. Here's astigmatism. When a ray travels through an optical system, it experiences all the aberrations simultaneously. The ray bends or traverses through the system because of everything that is happening to it at the same time. It's not seeing these aberrations one by one. It's not seeing them individually. So these figures, we are now studying them individually so that you get a sense of the shape. If the RIC curve has this shape, that means spherical aberration dominates the system. I'm very rarely going to have a case where the optical system has only one aberration, right? But from the shape, you will be able to tell which one of the aberrations is dominant in the system. So in this case, we are acting, or we have pretending we have designed a system which has no other aberration in it except for spherical aberration. So this is a pure spherical aberration curve, right? And so one point to note for a curve or for a system with spherical aberration is this anti-symmetric nature to the curve, right? The whatever is on the left half is going to be identical in magnitude to whatever is on the right half, right and left half. However, they'll be flipped. Okay, so that anti-symmetrical nature is this is something that you will see with spherical aberration. Okay. Now I can do the same thing, but I plot it for the sagittal rays. Okay. And now I'm plotting it, the transverse error here is the error or the how much the ray has missed the paraxial point, but now it's displaced along the x-axis and not along the y-axis, right? And you get a very similar curve. It's quite a symmetrical aberration. Now, what this set of curves is showing you, I can plot the RIC curves at any plane. Even in Oslo, you tell Oslo which is the image plane. Oslo doesn't automatically decide some plane is the image plane. You tell Oslo, put the image plane at this distance from my surface and look at the aberrations there. So you could look at the aberrations anywhere. You could look at the aberrations here. Of course, the aberrations will be enormous there. You're nowhere near the focal position. But if you so desired to look at it there, you could. So one thing is, by looking at the RIC curves at different planes, you can even tell which of those planes is the best focus. Right? So in this case, this graph over here is showing you the RIC curves, let's say the tangential RIC curves, at planes A, B and C. You can see they all have very similar form. They're all anti-symmetrical in nature. They all have very similar form. However, the curve at plane B has a region in between. So you could almost consider this region where the tangential error is 0. The transverse error is 0. And that's because these are paraxial. You're at the paraxial focus, and so you have the minimum error there. How do we define the longitudinal error? That was the transverse error, but how do we quantify the longitudinal error? So if you see in this figure, you have these rays incident and we have a convex lens. Yes. So his question is, since we define an aberration as the deviation from the paraxial image point, why would we even look at it at other planes? You look at it at other planes because you can sometimes get valuable information, and you'll see that the paraxial image plane is not necessarily the best image plane. And you'll see that as we go down this class today, right? So that you often need to move away from the paraxial image plane. If you're not at the paraxial image plane, then you are measuring the aberration as the displacement or the difference between any ray and the paraxial ray at that plane. That's how you would define it. Okay, so the longitudinal error, the RIC curves, if you're looking at an RIC curve, it's always a transverse error, right, that you're looking at. So the longitudinal aberration is measured as the difference between this distance, capital L, and this distance is where the further off rays come to focus, minus the paraxial focus, this distance here. So you can see in this particular case, this is going to be negative because capital L is always smaller than L dash. And this is undercorrected spherical aberration. So it's negative in nature, and it is typically what you see when you have converging or convex lenses. Okay. Now the longitudinal aberration is plotted slightly differently. It's plotted with it's not called a RIC curve because the rays are not intercepting the focal plane here. That's why it's not an intercept curve. Here you're measuring some distances along the optical axis. So on the x-axis, you are plotting the so the y-axis is the height of the ray. So for example, the paraxial ray would have height 0, and that's what you would plot here. And its error, so this is actually the error, the longitudinal error. So the paraxial ray has 0 height and 0 error, so it's plotted here. The next ray has this much of height, let's say h1, and it is focused, let's say, somewhere over here. So this is its error, right? So it's, well, maybe I should take a ray which is a little further off. Let's say, let me take this ray. So this has height h and it's focused here. So this is its error. Let's call that L1. So this maybe corresponds to the ray with height h1 and this distance corresponds to the error L1. Okay. So you're plotting along the y, slightly different from how, because normally we take the independent variable on the x-axis, but I tell you, these optics people always try to do things differently with their graphs. So the y-axis is your independent variable, it's the height of the ray, and the dependent variable is on the x-axis. Okay. And in this case, because we have a convex lens and the longitudinal aberration, because it's defined like this, it's always negative, the curve is bending this way. As you go further and further away, you can see this is the highest ray and it has the largest aberration, negative aberration. Okay. You should be, just by looking at these curves, now getting a sense of how you could do a correction. Because I'm saying in this case, I have the longitudinal error like this. Just intuitively, what should I add to this to make it a, what is the best case when I have no error? What should this graph look like? So if this is my longitudinal, the axis to plot the longitudinal error, and there was no longitudinal error, what should I have there? I'll have a straight line. All rays, no matter what their height, have error 0. So if this is what I have, how could I convert this to this? Pardon? I would, no, forget, there are other ways. I'm not talking about that. I'm saying intuitively looking at this curved graph here, how could I make this curved graph a straight graph like that? Not optically, what would I do? Mathematically, what would I do? You're still thinking, if you say move the screen, you're thinking optically. I'm saying mathematically, it of course has an optical implication. Wouldn't I just add a curve like this? If I could somehow add something into my system or do something, so when you say move something, change aperture, do something, maybe those things are adding this curve. If I could somehow, if my system has this shape, the error has this shape, if I do something to my system so the error now has this shape, wouldn't the resultant error be this? And that's one of the ways you correct. You add some other elements and you'll see what affects spherical aberration. So somebody said change aperture, and you can see that aperture clearly is one of the ways of correcting. Why? Because we have said that the rays that come from further away, these rays have of course the largest aberration. So if I were to put an aperture stop and block these, clearly I've reduced the aberration already, both longitudinal and transverse, simply because I've blocked rays, right? So yes, one way to reduce spherical aberration is to change the aperture. But another way to reduce spherical aberration, which may not be so obvious, is to change the shape of the lens. And what do we mean by shape of the lens? The shape of a lens is governed by its R1 and its R2. Now, since focal length is defined 1 by f n minus 1, 1 by R1 minus 1 by R2, I can change R1 and R2 such that f does not change, because finally I want my optical system to stay the same. But I can change R1 and R2 such that f is constant and yet with a lens of a different shape, you'll find the spherical aberration is slightly different. And that's a powerful tool that we have. Okay? And maybe I have to add some other lenses to my system, and we'll see. Again, I gave you a clue when I said under-corrected spherical aberration is what a convex lens sees. So you add a concave lens, and this is typical graph of a convex lens. This is a typical graph of a concave lens. Now clearly I'm not saying add two lenses of same power, then I remove the focusing ability of my system. But you will add a concave lens, adjust distances so that overall you get power in your system. But the concave nature of the lens you have added offsets and reduces the spherical aberration. So that is why looking at these aberrations with these curves is very useful, because the curve gives you an idea of what you need to do. Okay? Okay. If you look at an image which was taken with a system that had spherical aberration, what you would see is, or if make it simple and say if you were looking at an image of a point that with an image that had, with a system that had spherical aberration, the image should ideally also be just a point. So your object is a point, the image should be a point. But if the system has spherical aberration, you're going to see a sharply focused point with a kind of blurry circle around. Okay, those are these rays. So you can see the image point is here, but you do have rays over here. Right? And you have rays, we have not shown all of these rays. So you have rays all over here. Right? So you'll have a sharply focused point in the center and you'll have a blur over here. So that's what you expect with spherical aberration. That's how your image deteriorates. Okay. So one of the ways of looking at it is then to just look at the ray, and this is, you will do this when you do the lab today. You'll see the ray trace. So you have these fan of rays and how they intersect the plane, and these images are just showing you how the rays intersect the plane. So there's a concentration of rays in the center. These are the focused paraxial rays, but you do have rays in a larger circle outside, and they are there as part of your image, though you don't want them to be there. So this comes to the question someone had asked some time back: why would I move away from the paraxial focus plane? Well, if I look at the paraxial focal plane, this is how the spots are spread. But if I move, now this is the furthermost rays are being imaged here. The paraxial rays are being imaged here. So I have a spread. This whole region can be considered a kind of focal region. So if I move within this region, it turns out that there's one place where the spread of the rays is minimum. Here the spread is only this much, here the spread is this much. Even though a lot of the energy may be concentrated in this region, I still have this effect. Whereas if I'm in this place, the rays intercepting here is just this. So the central spot here, this spot may be much smaller than this spot here, but I don't have anything else outside. And so this, what is CLC? It is CLC because it's called the circle of least confusion. So you often will use your best image plane not as the plane where the paraxial focus is, but you will move to the center of least confusion, circle of least confusion. Now you can see if in Oslo or in some optical software you were asking to do an axial ray height solve, you always set the conditions for that axial ray height solve as move the next surface or choose the next surface to be where the axial ray height goes to 0. And that is going to be this plane. So you might do that, and when you start studying aberrations, you may see that's not the plane where the aberrations are least. So the solve might help you get to approximately where you need to be. You might have to actually do something else to get to the best imaging plane. Right? You might have to look for where the aberrations are less and choose that plane rather than the plane where axial ray height is 0. Okay? Okay. So I think that's all I wanted to say about spherical aberration. Coma. Now, coma is an off-axis aberration. What does that mean? It arises when you have rays coming from a point not on the axis. Okay. Again, for demonstration purposes here, we have a parallel set of rays coming from off-axis, but it could be that you had some object and you're looking at all the rays coming from this off-axis point. So they're not parallel, but they're coming from an off-axis point. Okay. Coma, spherical aberration, we said could be considered to be a variation of the focusing ability of the lens with aperture. Coma, on the other hand, is a variation of magnification with aperture. Now, all these parallel rays in an ideal system, if I had an ideal lens and I had a set of parallel rays coming, they would all focus at one point over here, right? This would be my ideal focal point. But you can see in the image drawn here, the two rays equidistant from the center, they are focused at the same point, that's this, but the paraxial is actually focused here. So there is now a transverse error here, and that transverse error is nothing but this. There is no longitudinal measurement of coma. The coma is always measured only in the transverse. Okay, so there is no longitudinal component. Okay. Coma is a terrible aberration because if you think about it, spherical aberration, you could kind of locate very easily the center of gravity of your image. You had a central spot and then there's a spread around it. But coma gets spread in this direction and not symmetrically, as you will see. So you have, so this is your object plane, this is your image plane, and then you have the lens in between. And what has been traced here is a set of rays all coming from the same object, off-axis object point, but these rays are all traveling through different regions of the lens. And they are, instead of all coming to the same image point, are each forming a different set of images in the image plane. Now, what happens with coma, and just to make it clearer, you can look at this figure. Assume this is your lens. Okay, so this is the surface of your lens, and at these points marked 1 to 4 and 1 dash to 4 dash, these are rays that are coming and hitting those points of the lens. What happens in coma is, look at this, you have 1, 2, 3, 4 and that repeats. In the image plane, rays 1, this ray 1 and this ray 1, they both focus at this point here. So the ray that hit the top of the lens and the ray that hit the same distance but below the optical axis, they both imaged the same point. So that's good. But the rays 3 and 3, ideally these rays, I'm showing you the location of the rays on the lens, but all these rays came from the same object point. Okay, so they're all coming from one point on the object. Ideally, all these rays must go to a single point in the image. But rays 3 and the rays marked 3 on the lens, they are forming an image here. So what lies on an annulus on the lens is forming a circle, not a point in image space. So rays 1, 2, 3, 4 form 1, 2, 3, 4 in the image space. And you can see that while I traverse these rays sort of, I have rays 1 and 1 again and 2 again. In this point, in the image plane, both the rays 1 come to the same place, both the rays 2 go to the same place, both rays 3 go to the same place, both of the rays 4 go to the same place, but none of these are the same place. Instead, they lie on a circle. So instead of getting a point, you're getting a circle. So for every point you should have got as an image, you're getting a circle. And that's why it's a terrible aberration. Now these rays 1 to 4 all lay on the same annulus of the lens. If I take another annulus, I get another circle, but that circle isn't centered about the same origin of the previous circle. It's slightly shifted and centered, which is why I can't have a nice center of gravity of my image. Whatever it was in spherical aberration, the image was centered. Here, the next set annulus here, which is 1 dash to 4 dash, they form another circle which is laterally shifted down. And because I've just pulled out the terms from the aberration polynomial here, you see an r squared here. So you see what goes around twice on the lens is going around only once over here. That's happening because of this r squared. So just for you to see why that having that general form of the aberration polynomial tells you something about the images. So every annulus on the lens is going to give you a slightly displaced circle here. You'll have another circle and so on, right? So you have this, it's called coma because it has this comet-like, the tail of the comet. That's the kind of image you get. For every image that should have looked like a point, you have like a comet-shaped image. Okay. Now, you can see that the tangential or the meridional rays are forming this image. Whereas so these are the tangential ray image, whereas these are the sagittal rays. Which are the skew rays of this system? So in this figure, 1 corresponds to meridional rays, 3 corresponds to sagittal rays, which are the skew rays of the system? Skew rays are the rays that do not traverse the optical axis. So which are the skew rays here? They are all skew rays except for the rays that are the meridional rays, right? So rays 4, 4 dash, 2, 2 dash, these are all skew rays, right? Okay. So the ray fan, if you look at the paraxial image plane, the ray fan is going to look like this figure on the left. The paraxial focus is down here and the sagittal focus, let me show you that. So the sagittal focus is here, the tangential focus is here, right? And it turns out, if you look at the way, these are the rays coming from one point on the object, one off-axis point on the object, but they're spreading out and forming this comet-like shape. Half of the energy is actually located in this region. So this, as a point of interest, this angle is always going to be 60 degrees, and we define the sagittal focus as, so in the previous figure, this is where the rays 3 would have come to focus. This is where the rays 1 came to focus. So we call this the sagittal coma. It's a measure of the sagittal coma. Capital H is a measure of the tangential coma, but since half of the energy lies in this region, the sagittal coma is considered to be a better measure of coma than tangential coma, okay, because more of the energy lies in this sort of triangular region over here. Okay. Now, I have plotted the RIC curve here for the meridional rays. Right. Why does it have this shape? If I look at the lens and with rays coming in over here, let's say this was the paraxial focus plane, these two rays did come to focus at the same place, right? So, let's assume these were both equidistant from the optical axis. So, these are in the meridional plane and they both come to focus at the same height. So, they have this, the error here, the error is always in this direction, correct? This is tan u. The rays have slightly different angles. So, for this ray it has some value, for this ray its value will be where they have the same height. So, this will correspond to one ray and this will correspond to another ray, right? But they both lie on the top, so they are both positive. So, here you see now a big difference between the RIC curve of spherical aberration and of coma. In spherical aberration, your curve had an antisymmetrical nature because in spherical aberration, the ray coming from the bottom, from the top of the lens, this was its error, so it was negative, but the ray coming from the same distance, the ray coming from the same distance below, it came up like this, so it had the same magnitude transverse error, but a sign was opposite. So, the two rays in spherical aberration, they have the same magnitude and opposite sign, but in coma they have same magnitude, same sign, right? So, the curve here is symmetrical in nature. It's not exactly the same because the tan u's are not the same. The rays have different angles coming in. But it's not antisymmetrical in nature. And here you should start getting the idea, if you are given the RIC curves of a system and you don't know anything about the system, just by looking at those RIC curves, you'll be able to tell this system is dominated by the aberration coma, this system is dominated by the aberration spherical, right? Because in one case clearly there will be antisymmetry and the other not. Okay. Now, I have drawn the RIC curve for the meridional rays. What would it look like? And it's positive, so we call this overcorrected coma, right? And this is sort of what is expected for a convex lens. What do you think the curve will look like for the sagittal rays? So that's correct. In fact, there will be no error. And if you also go back to the polynomial expression, see a lot of, right, you have sine 2 theta in this, right, and your theta for sagittal rays is pi by 2. So, this x term is going to go to 0 anyway, right. So, this is what you expect, okay. Okay, and this just gives you a side view of the rays coming in, and you can see these were all supposed to form one point, right. So, you can see how bad it is, right. Again, coma is an aberration that is affected by the shape of the lens. So, shape is one way to correct it. Clearly, aperture, stop position, aperture stop, size. So, I'll just say aperture stop because its position as well as its size will affect coma. Okay. Okay. I don't think I'll have time to go to the third aberration today, but what I will do is, so you can take So today's lab exercise is for you to understand aberrations better and to see also how you can correct aberrations. So we are only looking in this graph at two aberrations, spherical aberration and coma. And what has been plotted here is along the x-axis, you're plotting something called shape factor, which is a function of R1 and R2 of a lens. So you're taking a single lens, you're going to keep the focal length constant, keep f constant, but change R1 and R2. And you see that as you do that, these are the figures you see over here. All these lenses, the focal length of all these lenses is 100 millimeters. But you can see the shape has changed so much, right? And that is by changing R1. So R1 is varying through these parameters. Therefore, you'll have to calculate what is the value of R2 such that f stays 100 millimeters. But in all these cases, the spherical and coma has been, these aberrations have been calculated, and that is what is plotted. So the x-axis is plotting the shape factor, and the two vertical axes are plotting coma on this side and spherical aberration on this side. And you can see this is how spherical aberration varies for this lens, and this is how coma varies. And the interesting thing to note is that this place, you have not tried to minimize the aberration at all here. You're just saying, if I change the shape, keeping focal length constant, how do the aberrations vary? That's all. You're just studying that. But you see, there's a natural position, or rather a natural shape for which both coma and spherical aberration become minimum. And if you look at what that shape is, it's very close to a plano-convex lens. So if you have a plano-convex lens and light is incident from the curved side, that's also important. This is where you will have minimum coma and minimum spherical aberration. It's actually, the actual values is one radius of curvature 6 times more than the other one. But you can just use a plano-convex lens and get close to this behavior, right? If you turn your lens around and you use it like this, you will not get that benefit, okay? So this is the way to use a plano-convex lens and have the best case, that is the minimum coma and spherical aberration. Okay, so in today's class, we've started looking at the monochromatic aberrations more specifically, and we've covered 2, spherical aberration and coma. And what you will do in the lab later is to plot this graph. So you're going to have to generate these lenses, same focal length, varying curvature, and find the values of aberration and plot them, and you should see this behavior, okay?